Hello everyone, I'm Mohammadreza Armandpour from Texas A&M University, and in this talk I'm going to present our work with the title Partition-Guided GANs, which essentially improves unsupervised image generation using the GAN. Now let's start with the challenges of training a GAN. One of the well-known problems is mode collapse problem. That essentially means that if our data has several modes, sometimes when we use GAN to generate those samples, it misses some of the modes, as you can see here. But there is also another problem with GAN that we refer as mode collecting, which essentially means sometimes GAN produces samples between two modes, although the real data doesn't have any samples over there. In this slide, we present our main idea that how we solve the aforementioned problems. So learning a single generator to be able to estimate a very multimodal density can be actually a very challenging task. So what we do instead is we use several generators where each generator is only designed to generate samples for a specific part of the space. So our method consists of three parts. We first partition the space to have simpler distribution in each partition. Then we train a different generator on each part of the space. And because it's still possible that each generator produces samples outside of that region, we provide some guide to that generator to only keep its sample to that specific region. To alleviate the mode collecting problem, we actually should put this should manifold in different partitions. The reason for that is if we use a single generator to produce two disconnected manifolds, that generator, because it's a continuous function, it puts some mass density between the two disconnected manifolds, which is not desirable and creates mode collecting problem. Our differentiable space partitioner consists of three main components. First, we use recent successful contrastive learning methods to learn useful representation. And after that, we make a k-nearest neighbor graph in that space of representation. And by putting connected nodes in the same partition as much as possible, we partition the space. The last function of our space partitioner is presented in this slide. For more detail, please refer to our paper. My collaborator Ali continues the rest.
Thank you, Reza. Now that we have a partitioning for the space, we can train a different generator and discriminator on each of these partitions, and that would significantly reduce both mode collapse and mode connecting problems. And to overcome the extra computational cost, we will use weight sharing for both generators and discriminators. This would further allow information sharing across different partitions, which would be very useful if you have a smaller number of data sets in each partition. The only remaining point is to generalize the GANs loss function to this setup, which I'm showing the final results here, and the details of driving it can be found in the paper. Now that we have a differentiable space partitioner, we can use it to define a distance between every region and every point X. If you take the last layer's logits and define R as follows, you would have a very nice property of being 0 everywhere in the partition C, and the further away X is from that point, the larger the value it gets. If we add R as a penalty to the generator's loss function, we would be able to provide directional and gradients to G, even if for whatever reason, D is not able to provide that. And we can guide G towards this designated region. Combining these two tricks, you can see that we are able to recover significantly more modes. The plot on the left shows the cost surface for R. And as you can see, sometimes we have local minimas, which will fool generators to generate samples from parts of the space that it's not supposed to generate. To alleviate that problem, we propose an architecture and provide the necessary theoretical guarantees to avoid any local optimas for R. For details on the architecture and the theorems, please see the paper. But let's see how that changes things. Now that we don't have any local optimas, we would be reliably providing gradient all over the space. And as you can see, as a result, we are fully recovering all the 25 modes. Let's look at some empirical results on the famous data sets. On CIFAR 10 and Stoichkov, we achieve a state-of-the-art results, even beating supervised methods. Our method introduces a few hyperparameters, lambda, the penalty term, and k, the number of partitions. As you can see, our method is not hypersensitive to any of these parameters. Finally, let's look at results on larger data sets like SDL10 and ImageNet. We still achieve a state-of-the-art results, beating all previous unsupervised methods that don't use any augmentation. For more details and example of images, please see our paper.